Close your eyes for a moment. Imagine waking up tomorrow and discovering summer has been erased. Not delayed, erased. It's June, yet snow drifts across your fields. Frost clings to dead crops in July. The sun, when it pierces the haze, looks pale and wounded. Your children ask why the sky has changed. You don't have an answer. Food is running out. Rumors spread faster than the cold. This is not fiction. In 1815, the sky itself seemed to turn against humanity. Across Europe and North America, sunsets burned in unnatural shades of crimson and violet. Ash high in the atmosphere scattered the light into apocalyptic beauty. Beneath that beauty, crops failed. In New England, farmers watched corn freeze in August. In Switzerland, bread riots erupted as grain supplies collapsed. Mortality surged. Livestock starved. A creeping dread settled over entire nations. The cause lay half a world away. On the Indonesian island of Sumbawa, Mount Tambora had detonated with a force that defies modern imagination. The explosion was heard over 1,200 miles away. Pyroclastic flows, superheated avalanches of gas and pulverized rock racing faster than a commercial jet, incinerated everything in their path. The volcano ejected tens of cubic kilometers of debris into the stratosphere. Entire communities were erased in hours. Up to 100,000 people would ultimately perish from the eruption and the famine that followed. The ash formed a global veil, reflecting sunlight back into space. The following year would be remembered as the year without a summer. In Britain, the unrelenting gloom trapped writers indoors along Lake Geneva. Among them were Lord Byron and Mary Shelley. To pass the time beneath the darkened skies, they told ghost stories. One of them became Frankenstein, a tale about humanity attempting to command forces it barely understood. History has a sense of irony, and yet Tambora was only a warning shot. Beneath the Earth's crust lie reservoirs of magma so vast they dwarf any eruption recorded in human history. Supervolcanoes do not merely explode, they rewrite planetary conditions. Around 74,000 years ago, Mount Toba in Indonesia unleashed an eruption estimated to be dozens of times more powerful than Tambora. Ash blanketed much of South Asia. Global temperatures plunged. Some genetic evidence suggests that after Toba, the human population may have dropped to as few as several thousand individuals worldwide, a genetic bottleneck we may still carry within our DNA. Humanity did not dominate the Earth then. It barely survived it. Today, roughly 20 known supervolcanic systems remain active beneath the surface. Yellowstone in the United States, Campi Flegrei in Italy, Toba still simmering. These are not relics of a chaotic past. They are living geological systems, slowly accumulating heat and pressure. To grasp the scale, if Yellowstone erupted in a full supereruption, ash could bury vast regions of North America beneath meters of debris. Air traffic across entire hemispheres would halt. Global agriculture would falter under sudden cooling. Supply chains would fracture. The eruption itself would be catastrophic. The aftermath could threaten billions. For decades, scientists have monitored these giants, mapping tremors, measuring ground deformation, analyzing gas emissions. But monitoring is not mastery. It is vigilance without control. So the question emerges, quietly at first, then insistently. What if watching is not enough? What if survival demands intervention? Instead of waiting for these sleeping systems to awaken, could we disarm them? More audacious still, could we tap into their energy and turn a planetary threat into a planetary asset? One proposal, developed by engineers in collaboration with space and geothermal researchers. Imagines drilling a network of deep boreholes several kilometers into the rock, surrounding a supervolcano's magma chamber. Not into the molten core itself, that would be reckless, but into the stable outer shell where temperatures are extreme yet controllable. Cold water would be injected downward under immense pressure. As it travels through superheated rock, it would transform into steam, absorbing vast quantities of thermal energy before being pumped back to the surface. There, turbines would convert that heat into electricity. The volcano would become a geothermal engine. Positioning would be critical. Drill too close to the magma chamber, and you risk destabilizing the system. Drill too far, and the thermal gradient becomes insufficient. Real-time seismic monitoring, adaptive flow systems, and autonomous pressure controls would be essential. It would be among the most delicate engineering operations ever attempted. If executed carefully, the system could provide a continuous source of renewable energy for thousands of years. More importantly, the gradual extraction of heat could lower pressure within the chamber itself, potentially reducing the likelihood of a catastrophic eruption over geological timescales. It would not be a quick fix. Cooling a magma reservoir tens of kilometers wide could take centuries, but civilization is beginning to think in longer horizons, not election cycles, not fiscal quarters, millennia. Yet even neutralizing one supervolcano would not end the story. These systems are born from mantle plumes, columns of heat rising from deep within the Earth. They will continue to form as long as the planet remains geologically alive. Super eruptions may occur every 50,000 years or so. In cosmic terms, that is frequent. Learning to harness these forces could mark a turning point in human history. The difference between enduring Earth's volatility and shaping it, because supervolcanoes are only one layer of risk. From the molten lithosphere below to the atmosphere above, each component of our planet carries its own instability. Climate swings, ocean acidification, ice sheet collapse. Each layer interacts with the others in complex feedback loops. For the first time, humanity possesses tools powerful enough to influence these systems deliberately. Technology has given us the capacity not only to consume the planet, but to manage it. Engineers of a living world, custodians of geological time. And that responsibility begins with the most immediate challenge of all, the climate. Because if a single volcano can cool the planet for years, what happens when billions of tons of greenhouse gases warm it continuously? What if the sky itself becomes our next engineering frontier? And what if the answer to saving Earth requires us to alter it in ways we never have before? If we are willing to drill into a supervolcano, are we also willing to dim the sun itself? And who decides how much light the world receives? In 1991, nature accidentally saved us and showed us exactly how to do it again. When Mount Pinatubo erupted in the Philippines, it hurled nearly 20 million tons of sulfur dioxide into the stratosphere. Within days, the gas spread across the planet, forming a thin, reflective veil high above the clouds. Sunlight that would normally warm the surface was scattered back into space. Global temperatures dropped by roughly ½ degree Celsius. For almost 2 years, the Earth cooled. The rise of sea levels briefly slowed. The fever broke, if only temporarily. It was as though the planet had applied sunscreen. For climate scientists, Pinatubo was more than a geological event. It was a demonstration. Proof that the atmosphere could be altered in ways that produced immediate global consequences. And today, as heat waves intensify from California to southern Europe, from Pakistan to Australia, that demonstration has taken on new meaning. In Britain, the summer of 2022 saw temperatures exceed 40 degrees Celsius for the first time in recorded history. Rail lines buckled, wildfires tore through suburbs. The Thames receded in places, exposing cracked riverbeds. A country built for rain found itself confronting heat it was never designed to endure. If volcanoes can cool the planet by accident, could we cool it on purpose? The proposal is known as stratospheric aerosol injection. Aircraft, high-altitude drones, or specialized balloons would disperse measured quantities of sulfur dioxide into the upper atmosphere, mimicking the reflective haze produced by volcanic eruptions. The particles would linger for months or years, reducing the amount of solar radiation reaching Earth's surface. The physics is compelling. A relatively small mass of reflective particles can offset the warming effect of vastly larger quantities of carbon dioxide. In theory, a coordinated program could lower global temperatures within a few years, far faster than transitioning the entire world away from fossil fuels. To leaders watching coastlines erode and crops wither, that speed is intoxicating. But climate is not a thermostat with neat, uniform settings. It is a turbulent, interconnected system. Cooling the planet on average does not guarantee balanced outcomes everywhere. Monsoon cycles could shift. Some regions might experience drought while others face flooding. Agricultural belts that feed billions could destabilize, and there is a deeper risk. If aerosol injections were maintained for decades while greenhouse gas concentrations continued to rise, the atmosphere would become dependent on artificial shading. Abruptly halting the program could unleash rapid temperature spikes, an effect known as termination shock. Imagine decades of suppressed warming released in just a few years. Coastal cities inundated not over centuries, but within a generation. Crop failures cascading across continents. We would be trading one catastrophe for another, buying time with a planetary debt that compounds with interest. Beyond physics lies power. Who decides the planet's thermostat setting? If one nation deploys aerosols to protect its agriculture and another experiences failed rains as a consequence, is that an unfortunate side effect or an act of aggression? If cooling strategies benefit the Arctic but plunge temperate regions into harsher winters, who bears responsibility? The sky, once neutral ground, could become both weapon and hostage. For some scientists, the risks of altering Earth's atmosphere directly are too great. Their gaze turns outward to space. At a gravitational balance point between Earth and the Sun lies a region where objects can maintain relative stability. There, engineers have proposed constructing a vast solar shield, designed to reduce incoming sunlight by less than 2%. That small reduction could theoretically return global temperatures to pre-industrial levels. The scale, however, borders on incomprehensible. We are talking about a structure larger than Argentina, weighing millions of tons, assembled in orbit by autonomous machines, potentially costing more than $1 trillion. And if a single calculation is wrong, if the shield drifts, fragments, or blocks too much light, we could tip the climate in the opposite direction and trigger dramatic cooling. Engineering at this level would demand a precision never before attempted on a planetary scale. Some concepts envision trillions of silicon-based microstructures, forming a diffuse cloud rather than a rigid disk, flexible, adjustable. If temperatures fell too far, the swarm could be thinned or repositioned. Others propose fleets of orbital mirrors capable of redirecting sunlight, reducing it in warmer decades, increasing it during cooler eras. Humanity would not simply endure climate cycles. It would manage them, yet the cost and coordination required would redefine global cooperation. Launching the materials alone would require unprecedented space infrastructure. Governance mechanisms would need to prevent unilateral action. A planetary shield would not belong to any one nation. It would demand trust on a scale history has rarely achieved. While some look upward for solutions, others argue that the most powerful tools already exist here, woven into the biosphere itself. Large-scale ecosystem restoration has emerged as one of the most grounded forms of climate intervention. Reforestation initiatives across Africa's Sahel aim to establish a vast belt of vegetation stretching thousands of miles. Beyond absorbing enormous quantities of carbon dioxide, such projects combat desertification, restore soil, strengthen food security, and generate livelihoods. Trees do more than store carbon. They shape rainfall patterns. They cool landscapes through evaporation. They anchor ecosystems in stability. Protecting natural carbon sinks may be even more urgent. The Amazon rainforest cycles immense volumes of moisture and carbon each year. Its preservation acts as a counterweight to industrial emissions. If lost, warming could accelerate beyond projections, as stored carbon floods back into the atmosphere. But restoration alone may not offset the scale of human emissions. Advances in genetic engineering are beginning to reshape the biological foundation of climate strategy. Scientists have modified the internal mechanics of photosynthesis in experimental crops, increasing growth efficiency significantly under controlled conditions. More biomass means more carbon captured. Algae are being engineered to convert sunlight directly into clean-burning hydrogen fuel. Microorganisms have been reprogrammed to generate electricity from wastewater and organic sludge, transforming waste into energy. The line between natural and artificial is dissolving. Perhaps the most dramatic proposal involves editing the genes of modern Asian elephants to reintroduce cold-adapted traits from the extinct woolly mammoth. The goal is not spectacle, but stabilization. Picture herds of mammoth-elephant hybrids roaming Siberian tundra, their immense weight compacting snow into dense layers that insulate permafrost beneath. By preserving frozen ground, vast reservoirs of trapped carbon could remain locked away. It sounds like science fiction, but so did splitting the atom until we did it. Each of these strategies reflects a profound shift. Humanity is no longer merely adapting to planetary systems. It is contemplating deliberate redesign.